Alrighty, good evening, Honors Math 2 students. This is your teacher reporting live from her dining room. We are going to go through exponential functions today, okay? An exponential function has this form. Y equals AB to the x power, where a cannot equal 0 and the base b is a positive real number other than 1. So b is a positive real number other than 1. So you can't have 1 as your base, okay? A is not 0 and b is not 1, basically, and b is positive. An exponential growth function happens if your a value is greater than 0 and your b value is greater than 1. Okay? And then your b value is your growth factor, the b. And if you have an exponential decay function, that's kind of the opposite there. I'm just looking for, there we go, where, a is greater than 0 still, okay, and your b value is greater than 0 but less than 1. So basically it's a fraction. And then if you have a exponential decay function, you have a decay factor. So that's your b value. B value turns into your decay factor. Okay? So this is what an exponential function looks like over here. Okay, there's a few properties. We're going to make a table to help us graph it. But an exponential function has something called an asymptote. Okay, the x-axis is an asymptote of the graph. An asymptote is a line that the graph approaches more and more closely, but it never crosses. So you'll see since you can't have 0 in your function there, that is why it has an asymptote. It's going to get close and close and close to the x-axis, but it will never quite cross it. So the graph rises when you have a exponential growth function. It rises from left to right, passing through the points 0, 1, and then 1 and whatever your b value is. Okay. When you have a decay function, the graph falls from left to right, but it still passes through those same points, 0, 1, and 1 and whatever b is. So exponential growth, teacher. Yep, 1. It's totally 1. Nope. Okie dokie. So now we're just going to evaluate. We're plugging stuff in, and you can do this. This is easy peasy. So evaluate the expressions for a and for b. So for a, we're going to replace x with 3. So this one turns into 3 to the third power, which is just 3 times 3 times 3, which is 9 times 3, which is 27. B says x is -2. So now we're going to do 3 to the -2. So can't have a negative exponent. So we're going to put it on the bottom. 3 squared, 3 times 3 is 9. So you get 1/9. So this one, for part A, we have 1/2 to the third power. So we're going to share that exponent. So we're going to have 1 to the third over 2 to the third, which is 1. Oh, it scared me. Heard noises. I thought someone was trying to bust in. I just watched a really creepy movie, so yeah. So 1 over 8. Okay. B, we have 1/2 to the negative 2 power. Now this one, you have options. You can share it and then switch it, or you can switch it right away. It's your call. But we're going to share that negative exponent. So you have 1 to the negative 2 over 2 to the negative 2. And then we're going to switch it. So we have 2 squared over 1 squared, which is 4. 4 over 1, which is just 4. So we're just replacing each of the variables with what they tell us to, and then we're evaluating it one step at a time. Now this, you might think that you could just say 24 to the x. Don't do it. Don't do it. It's not what we do. So 6 times 4 to the third. 4 to the third power. Now here's where my tired brain is going to use a calculator because I'm tired. 4 to the third power is 64. So we're going to have 6 times 64. And remember, you're using your calculator for that. You're hitting 4 and then that button that looks like a tent and then to the third power. So then we're going to go 64 times 6. Okay, and you get 384. Part B, we're going to raise it to that negative 2. So can't have a negative exponent, so 1 over 4 squared. 4 squared is 4 times 4, which is 16. And then when you multiply a fraction, you multiply straight across the top and straight across the bottom. Oh, I think we can reduce this. Let's try dividing by 2. So we'll get 3 over 8. And we want to leave it as a fraction. All right, last one for this part. We're going to plug in 3. 3 to the third, we had 27. Minus 7 is 20. And then part B, we're going to plug in a negative 2. So negative 2 can't have, so 1 over 3 squared. That's 1 over 9. Ew, we gotta subtract with a fraction. So we're gonna need a common denominator here. So me thinks it's gonna be 9. What do you guys think? So I'm gonna multiply top and bottom by 9. 1 over 9 minus 9 times 7 is 63. So we're going to be left with a negative 62 over 9. I don't think 62 divides by 3. Nope. So we are done. That is as far as we can reduce. Okie dokie, hokey pokey. Yeah, that's it so far, which is super crazy because that doesn't match with the book at all, but that's okay. We're good. All right. Let's check back. Silly B has to lied. Okay, now what we're going to do is we're going to graph. Okay, so we're going to plug it in, make a chart, all that good stuff. We're going to use a really cool property. Remember, every exponential growth and decay function goes through the point 0, 1, and 1, and whatever your b value is. So that's pretty cool. We'll keep that in mind. So this guy here, first of all, we got to identify if it's growth or decay, and we're going to look at the b value, the base. So in this case, our b is 2. And that b is greater than 0. So because it's greater than 0, this is a growth function. I think it's 1 actually. I feel weird about it being 0. Let's be greater than 1. So b is greater than 1. Okay, so this is a growth function. This one, b, is 1/2. And that is between, b is between 1 and 0. So this would be a decay function. Growth functions rise from left to right. So we can kind of keep that in mind. Yeah, we can put some negatives on there. You know, you don't really have to. We'll just kind of put -1. We'll do that. We don't want to go too crazy because you're going to get some really small fractions. And then we have 0, 1, 2, 3, 4. Okay, 2 to the -1 power is 1/2. 2 to the 0 power, anything to the 0 power is just 1. And there's our 0, 1 point we kind of knew was coming. 2 to the first power is just 2. 2 to the second power is 4. 2 to the third power is 8. 2 to the fourth power is 16. So, very cool. So we're going to graph those points. We're going to graph -1.5. So we go up halfway. We're going to go 0, 1, 1, 2, 2, 4, 3, and that's all I can graph right there. So my function, remember it's got an asymptote, so it does not hit that x-axis, or cross it rather. And there you go. That is my growth function. Let's do my decay. Now this one, you're going to have fractions. It's kind of unavoidable. It really wouldn't help us to graph stuff that divides by 2 because we're raising it to a power. So let's just kind of keep that in mind. Okay, so this one's going to fall. So we want some more negatives. That's pretty cool. So let's kind of even it out. So we'll go -2, -1, 0, 1, 2, and 3. Okay, 1/2 to the -2 power. That basically kind of flips it, you know what I mean? But you'll have 1 to the -2 over 2 to the -2. So it flips. You'll have 2 squared over 1 squared, which is just 4. If that was a 1, it's kind of the same deal. You're going to have to the -1 power. So you're just flipping it and you're getting 2 over 1. 0, anything raised to the 0 power is 1. 1, raising it to the 1 power is 1/2. If you square a half, you actually get a 4th. And then if we raise it to the 3rd power, you get an 1/8. Because you share that exponent, 1 to the 3rd over 2 to the 3rd. All right, let's graph it. -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4. See, I'm getting real close. And 1/8, so here's my decay function. All right. Okay, now we got to write a model. So the formula for exponential growth is, hold on, I don't want recursive rule. Oh my goodness. Yep, this is the question. There it is. I think it'd be, there it is. Exponential growth model, formula, whatever, is, I wonder, okay. So y equals your A value, which is your initial amount, I believe. It doesn't say on there, but yeah. Times 1 plus your growth rate raised to the t power. That's what we're going to do in this one here. Okay, so, yeah, that's the initial amount. That's A. So A is your starting amount, or initial. R is your percent of increase. If it was a decay function, it'd be decrease, and that would be a minus. And T is time in years. Okay? So, we want to write an exponential growth model that represents the population Y, T years after January 1st, 2000. Find and interpret the Y value when T is 7.5. Okay, so our function here, we have a starting amount. The population of the country was that amount, so 6.09, so that's your A value. And the population increased, so we have a growth model here. So we're going to go 1 plus, and if this is your okay, sorry, that's 1%. I don't know what confused me for a minute. So if that is your percentage, we have to turn it into a decimal before we can use it in the problem. So 1.18%. I take that decimal and I move it 2 spaces to the left. So you get 0.0118. That is my percent of increase or decrease. And then we're going to raise it to the t power. There is my model. And then I can go ahead and add that together. There we go. This one says 118. I forgot a 1. There we go. All right, there's my model. So now they want me to estimate when the population, find and interpret the Y value when T is 7.5. So right here, this represents the population T years after January 1st of 2000. Okay, so we want to interpret the Y value when T is 7.5. So that would be 7.5 years after that year. So that would be January 1st, 2006, I believe, about halfway through. Oh, never mind. You can't think of it that way. Nope, don't think of it that way. Because it's the amount of years after that year, which still confuses me, but here we're at. So, find and interpret the Y value. So we're going to plug it on in. And we're going to make that T 7.5. Okay, so we're just replacing the T with 7.5. And when I do that and plug it into my calculator using parentheses and using that little caret button, so I would have to type it in just like this with parentheses, and then I would hit that caret button to the 7.5. So when you do that, you get a population of about 6.65, and this is in millions. Okay, so that would be the population 7.5 years after that. So using this model, you can estimate the mid-year population in 2007. So it's, it would be 7 years past that date. So this is the mid-year population, 7.5 years past 2000. So halfway between that one. Yeah, so halfway between the year 2007 and 2008. Because 7 years since 2000 would be exactly 2000. 7.5 years would be halfway. Okay, so we're just making a model and plugging it on in. Then we want to estimate when this is actually a graphing calculator question, but we don't really do that. So, I mean, you can plug stuff in and get as close as you can, but you really want to do this with a graphing calculator. So this will probably be something I show you when I get back. So this is a graphing calculator question. What you would do is you would actually graph this function that you made. Okay, and then you would graph this function. And you would use a calculate function on the graph to see where they intersect. So don't worry about that for now. Holy cow. Well, right here, when we had our growth formula, we had 1 plus r. And that r represented our percent of increase. Okay, another thing we got to do is you have stuff here that's written kind of in a different form. Okay? So you'll look at these these fractional exponents. And what we're going to do is we're going to use our exponent properties to rewrite this. We want to tell whether it shows exponential growth or decay. And in order to tell that, I have to be in this format. Okay, and right now I'm not in that format. There's a whole lot of other stuff going on with my exponent. So in this one, you can kind of see that something kind of got lumped together, okay? What I can do, since I have a 4 in the denominator, I can rewrite this. Jeez, sorry, I hope that didn't mess anything up. I can rewrite that. And the t to the t over 4 can turn into t times 1/4. And because it is a power to a power rule like that, I can kind of assume that my two exponents got multiplied together. And that only happens when you have a power to a power. So I can take that 1/4 and I can just stick it on that 0.96. So I can change this to 0.96 to the 1/4 times t, because it is a power to a power rule. Okay, so whenever you have a denominator and a numerator, you're going to kind of pull them apart. So whatever's in the denominator is going to turn into a fraction, and that's going to go with whatever's inside the parentheses, and your variable stays on the outside. Because now I can evaluate this. 0.96 to the 1/4 power gives you, I think it's 0.99. Yes, it is. Approximately 0.99 to the t power. So now this is in the proper exponential growth function formula, and you can see clearly that this is exponential decay, because this is your b value, and your b value is between 1 and 0. So this is exponential decay. and your percent of increase or decrease. To do that, remember way back in the beginning, right here, in this case, we know it's decay because that's a decimal. So I can change that. Inside, to get that, what they did is they went 1 minus r, and they got 0.99. So if I reverse that, okay, then I divide, I get a percent of decay, percent decrease of, oh, I hope that recorded. Oh. I'm a little worried that didn't record because I wrote it way down there. So I'm gonna go back up here. Okay. So I know that's going to be exponential decay because that b value is between 0 and 1. If I want to figure out what the actual percent increase decrease is, since it's decay, that middle area was gotten by going 1 minus r, your rate, your percent of change. And we got 0.99. So if I solve that, that's going to tell me my r value is 0.01. So we've got a 1% decrease. Okay. All right, let's do this guy here. So this one, there's a subtraction involved. This one was multiplication, so that told me power to a power. This one's subtraction, so that tells me my quotient rule. To do the quotient rule, you would have to have the same top over the same bottom. And you always go top minus bottom, okay? So what we'll do here is we'll kind of evaluate what we can, and I'm just trying to see how they got 0.75. Okay, they kind of made a jump there. Evaluate the power and simplify. 1 over, okay, I get it. 1 over 1.331. There it is. Okay. Yeah. The book jumped some steps. So we put it back into the quotient. That's what we did. So if they subtracted, it means, remember, your exponent rules tell us we take the top minus the bottom. So the t was the top, the 3 was the bottom, and they subtracted because they had the same base. So now what we do, we can kind of play around with this a little bit. This is the same as that. Okay, and I don't want to deal with fractions. I want it to be written in a form that I can clearly see its exponential growth or decay. So to do that, I'm going to separate this fraction. I'm going to change this to 1 divided by 331 times your top. Okay, you can kind of pull apart those. So you're pretending someone multiplied those two fractions together. So we're pulling it apart because now this one, I can actually put in my calculator and calculate. So I actually get about 0.75 when I do that. And then I still have that other part. See, we just put it in the exponential form. And now I can see that my A value or my B value is greater than 0 than 1. Maybe issues. So this is a exponential growth. And it's the same deal. If I want to figure out the percent of increase or decrease, now The inside parentheses area would be 1 plus the rate. And I ended up with 1.1. So I'm going to subtract. So I get a growth rate of 10%. 10% growth. Okay, so you're going to do your best on the homework. And yeah, if you have questions, ask. Good luck, guys.